A system consists of two identical cubes, each of mass m, linked together by the compressed weightless spring of stiffness x. The figure is given. The cubes are also connected by a thread which is burned through at a certain moment. Find at what values of delta L, which is the initial compression of the spring, the lower cube will bounce up after the thread has been burned through. Okay, so this is a classical energy conservation problem. So let's consider the final state of this system, which will be something like this. This block will stay there, the spring will be extended, and there will be this block here. Okay, and let me just fill that up. It looks more better. Okay, so, and this is the final state. So let's consider that the extension in the spring is d. Okay, at this state. So this is mass m, this is also mass m. Okay, so it's kind of like that. I've drawn it at the same level almost. This is the same level, but it's okay. And let's assume that this height is h. Okay, and you might say that this block has a velocity, but I'm considering the extreme case where this block is given such a compression that when it just stops, and at that moment this lower block just bounces. Okay, just pulls up. Okay, so let me draw the free body diagram of this body here, this block. So that block at this moment, at this instant, it will have an upward force from the spring, which is equal to the stiffness of the spring, which is equal to x, times the extension in the spring, which is equal to d. So that's xd. And there's also its own weight, which acts always, and that will be equal to mg. And you might say that there will be also a normal force from the ground, but remember what they're asking, that the lower cube will bounce, right? It'll just bounce up. So for it to just bounce up, the normal force from the ground should become 0, right? Because you kind of feel weightless when you're just about to bounce up. So I consider that the normal force must be 0. Okay. So at this instant it doesn't have any velocity, and neither is it moving anywhere, so these two forces must balance up, right? So xd should be equal to mg. So from here we get that that d is equal to mg over x. Okay, so let's move on, and now I'm going to apply the conservation of energy. The initial energy should be equal to final energy, and that's because there is no non-conservative force acting on the system. There's only gravity, there's only spring force. Both of them are conservative, so we can apply the conservation of energy. So if I call this position as my u equals 0, which implies that any particle at this position will have a potential energy of 0. I define that for my simplicity. Okay, so let's make this aside. So what is the initial energy then? Initially this is compressed by delta L, right? So the energy stored in the spring initially is 1/2 times the stiffness or the spring constant, which is x, times the compression squared. Compression is delta L squared, and that is my initial energy. And there is no potential energy because this particle is at the place where I called u to be 0, where I called potential energy to be 0. And you might say that this block here will have potential energy, and I agree with that, but you have to agree with me that the initial and final state of the lower mass is the same. So even if I include the energy of this lower block here, that will automatically get cancelled, right? So I don't need to worry about it. Okay, so this is my overall initial energy, and that should be equal to the final energy, because which is equal to this mass here, the top one has gained potential energy, right? It has no kinetic energy because I'm considering the extreme condition. So this mass has come up by a distance of x, so it has potential energy associated with it, which is equal to mgh. And the final, there is also the energy stored in the spring, because there is also an extension of d here. So the energy stored in the spring is, in the final instant, is 1/2 times the spring constant times the extension squared. Extension is d, so it is d squared. Alright, and if I draw a cleaner diagram here, let's say that this is the natural length position of the spring. So initially this block is right here, and finally this block is right here, right? So this spring is compressed and this spring is expanded. So I've just drawn the initial and final position of both of these blocks. So this is h, right? Let's see if I can draw some lines. Okay, so this distance here totally is h, and this distance is delta L, right? And this distance right here is d. I assume that is the extension in the spring in the final state. So you can see geometrically that h should be equal to d plus delta L, right? So that is going to help us. Okay, so yeah, so let's substitute d back now here. D is this mg over x, so let's substitute that, and I'll also make this aside here. Okay, yeah, half x, for now I'll call it L because it's kind of tedious to write, is equal to mg times h is d plus delta L. That's what I said there. H is d plus delta L, for which I'm calling as L, plus half x times d squared. Now d is mg over x, so d squared will be m squared, is going to be m squared g squared over x squared. Okay, so we have everything in place. We've got it quadratic in L, right? You can see that. So we just need to solve for it now, but before that, let's simplify it a bit. So I lose one of my x's here, and this becomes just an x. Let's see what else. No, I don't see anything else. So let's multiply both sides by 2. So we get xl squared is equal to 2mgd, and I'm going to open this bracket, 2mgl plus m squared g squared m squared g squared over x. So let's simplify this further. I'm going to write the variable in pink, so as we know that this is a quadratic in L. So this becomes x times L squared minus 2mg times L minus I can take mg factor, I can factor out an mg, right? And inside I will get what? Let's see. Inside I'll get 2d plus mg over x. Okay, so that's what I get. Let me check if I have done everything right here. So this is our initial energy, this is our final energy, and I equated those, and I renamed delta L as L. So this became half x L squared is equal to mg times d plus L. We saw that geometrically is plus half times x times d squared, which is m squared g squared over x squared, but we lost one x there. So yeah, everything looks fine. Then we multiply it by 2, so we get this. Yeah, it seems right, and this becomes m squared g squared over x. Okay, alright, now we got to solve this quadratic. So I hope you remember the quadratic formula. So L will be equal to minus b is 2mg, plus or minus the square root of b squared. B squared is let me write it in green. B squared is 4m squared g squared. Let me extend this. B squared minus 4ac, 4 a is x, times 4a times c, which is negative mg, so this becomes a positive. So 4x mg times 2d plus mg over x. Wait a second, how did I got left out with the d? Oh my god, I had to substitute d as mg by x, so I'll substitute it now, but let me finish this right here. All of that over 2a is 2x. Okay, and now I will substitute d as mg over x, so I get 2mg over x. So basically this becomes this becomes 3mg, right? I'll write it over here. So this becomes a 3mg over x. Okay, and if we multiply this out, we will lose another x here. That x is also gone. And if we also simplify this, let's see, this will be 4 times 3 m squared g squared, and we lose all of this. We lose all of this. Okay, and now let us finish this off. So this becomes 2mg plus or minus the square root of 4m squared g squared plus 12m squared g squared, that is 16m squared g squared over 2x, and that is equal to 2mg plus or minus 4mg over 2x. So that is equal to I'll write two solutions because there is plus or minus. So 2 plus 4 is 6 mg over 2x, or it is 2 minus 4, which is negative 2 mg over 2x. So this is equal to 3 mg over x, or negative mg over x. And I believe that there is no way to accept this. A compression cannot be negative, guys, so we just reject it. We don't need it. So our final answer is 3 mg over x. So that is our first part, and I'll do the second part in the next video.